economics fanciers. Here today, I would like to talk to you just a little about elasticity. Already enthralled by the topic you've never before seen, you might be asking yourselves, what is elasticity? Well, let's hold off on the economics for just a second, as I think should always be the case. Let's look at this circular piece of rope I have tied together. Now, you'll notice its circumference, if I tug on it, it's hardly changing at all. It's staying about the same. You might say that with regard to my tugs, it is pretty inelastic. It's not getting bigger at all. Now, on the other hand, let's take this rubber band here. Its circumference is small now, but if I tug on it, it's getting big, right? So you might want to say, with regard to my tugs, it is elastic. I hope so. It's made of rubber. Look at that. So now we're going to bring it into an economics context. So before I was talking about it with tugs, but in economics, really, we're all about that change in price. So say you got a consumer consuming some good, but then the producers increase the price of that good, then evidently you would expect the consumer to buy less of that good. If they do end up buying less of that good, that means that good has a higher elasticity of demand. A small change in price will result in a pretty big change in demand. But, say that good would be relatively inelastic, that means the producers can change the price however they want, and the consumer is still going to buy pretty much the same amount of that good. So let's hope that's not the case. So now we're going to get into how you define elasticity. I was previously planning on using green, which is the color of money, but it didn't show up well on the board. So instead I'm going to have to be using this bold black. Let me take you in close. It's taken everything I've got just to get this board standing. Look, you see this box, 2 boxes of chalk, and the Holy Bible. Our economics textbook. So, like I said, how are you going to measure elasticity? Well, I'll draw this mysterious looking graph. The axis is labeled quantity, and probably didn't know that was coming. Price. So we got our demand curve right here. Now, you may be tempted to look and say, oh, maybe the elasticity is the slope. But let's not do that. That's going to give us units, and it's going to give us the rate of change. That's not elasticity. That's not what we want. What we want is something unitless that really tells it gets to the meat of elasticity. We want the percent change. Elasticity is defined as the percent change in quantity over the percent change in price. Now, recall that the percent change in any quantity, for what we could do, the percent change in quantity is equal to Q minus Q sub 1 all over Q. That's just the original minus the new over the original. Well, and this is right here, this is really just delta Q. So we can rewrite this as delta Q over Q. And we could do the same thing for price. We could write it as delta P over P. And, come down here. If we simplify that, what we're going to end up getting is that the elasticity is equal to change in quantity over, it's a pretty poor delta, change in price times the price over the quantity. And this is the price over the quantity at a specific point. The thing about this version of elasticity is that it requires 2 points. You can't just get the elasticity at a single point with this method because the change in quantity over the change in price are always going to need 2 points. They're always going to be finite. Now, later in the video, I'm going to show you how to get at a single point using none other than calculus itself. But for now, let's not worry about that. So guys, we're going to do an example calculation here for your troubles. We want to find the elasticity between these 2 points. So we're just going to plug it right into the formula. Change in quantity over change in price times price over quantity. So going from, let's do this point to this point, we have the change in quantity, which is 3 minus 2, over the change in price, which is 2 minus 3, times, oh no, look at this. This says we need P over Q, like, that looks like a single point. Well, we have 2 points, so what we're going to need to do is average them. Well, you average 3 and 2. In both cases, what are you going to get? You're going to get 2.5, and it's going to be the same on the top and the bottom. So that'll just go to 1. We don't need to worry about it. So our elasticity here is equal to 1 over negative 1, which is equal to negative 1. Oftentimes when dealing with the elasticity, you'll take the absolute value of it, but it doesn't really matter. It is worth noting that had I picked a different region on this curve to mess with, the elasticity would not have been constant. It would have been different if I did it up here or down here. If I did it at this higher portion of the curve, the elasticity would have been higher, whereas if I would have done it on this lower portion of the curve, the elasticity would have been lower. And that kind of makes sense, you know? You expect if the price of someone's good is super high and then the producer lowers it, people are going to jump at that opportunity. But if it's like 5 cents and they lower it to 4 cents, like, who cares? It's already 5 cents. That's not a big deal at all, that 1 cent difference. So now you can go and woo your friends with these economics calculations, hopefully gain much fame. Now that I've gone through that, I'd like to talk to you a little about what they call tax incidence. And it sounds fancy, but really it just refers to the burden of the taxes. Like, who does it fall on? If you have, say, the government puts a tax on some good, and the supply of that good is relatively inelastic, but the demand of that good is elastic, well, that means the consumers can change how much they're consuming, but the suppliers, they don't want to change how much they're supplying, so a lot of the burden is going to fall on the supplier. And if you flip that scenario around, say, suppliers are producing good, but they have an elastic supply, so they can change it as much as they want, but the consumers, you know, they have an inelastic demand, so they can't change it. They're going to be buying a lot more of that taxed good, so the tax is going to fall mostly on them. Now, in the third case would be when the price elasticity of demand and the price elasticity of supply are equal, in which case the burden of the tax is shared upon the consumer and the producer, and it can vary depending on the situation who takes more of it. Now, I like to think myself a very honest person. When I first chose this topic, the very first thought that popped into my head was, I can make an integral out of this. But I've already made an integral out of something in economics. I want to do something different. So in this tutorial, I'm going to make a derivative out of this, which is, for all intents and purposes, probably much simpler and easier to explain. Actually, in this video, I will not be explaining where the derivative comes from. We're just going to use it, and you're going to have to take my word for the power rule. In any case, we're also going to use a limit. So before, we were working with the arc elasticity, which is actually, in more advanced economics, much less common. What they like to use is called the point elasticity, which, unlike this, does not require us to average 2 points together. It only requires 1 point. And the point elasticity uses the ideas of calculus, specifically the limits and the derivative. So what you do is, you might expect this, you just take the limit as the change in price approaches 0. of delta Q over delta P times P over Q. And what does that equal? Well, that's just the derivative. That's just the differential dq by dp times a single point. Since this is the slope of the function at a single point, we only need one point here. So let's see if we can use that in a calculation. Say we have some graph, and it's not a linear demand curve, which we haven't really dealt with for the most part, but let's suppose it is. Let's say the quantity is equal to some constant k divided by the price to the nth power, which is just another arbitrary constant for the sake of generalization. Well, if we take the derivative, you're just going to have to take my word for it. You're going to get k, you got to do the power rule, n's in the denominator, so you go negative n divided by p to the n plus 1. Now, I don't have the formula up here, but it's fine. You should There we go. If we take this and multiply it by p over q, you get negative kn over p to the n plus 1 times p divided by q. But what is q? Well, we have q right here. It's k over p to the n. So I'm going to have to move my chalk here so you can see. The whiteboard would be less stable. This is equal to negative kn, but you have to flip this fraction because it's in the denominator. It becomes p to the n plus 1 divided by p to the n plus 1, and this k becomes in the denominator. Well, you'll see that those k's cancel and the p to the n plus 1's cancel, and you're left with negative n. So rather unintuitively, if we have a linear demand curve, the elasticity varies across different regions of it. But if you have this nonlinear, funky-looking inverse relationship, it turns out that the elasticity of price or demand is actually constant everywhere, and it's equal to the power that the price is raised to. I think that is very intriguing. Far more intriguing than most things I encounter in this illustrious field of study. So you have some good, and the consumer is consuming that good. But then the producer jacks up the price. Well, odds are the consumer is going to want to buy less of that good. And if they actually end up buying less of that good because of the jack up in price, you're going to call that good's elasticity of demand inelastic. No, it's the other way around. This makes me so mad.